To answer this question, how many meter sticks does it take to go mass of the moon? I'm going to give you some info. I'm going to let you know a couple things about a meter stick. First of all, here's a freebie. It's a meter long, okay?
No way.
Here's the next thing. A meter stick has a mass of 0.2 kilograms, okay? And it's 1 meter. I'm going to give that to you, like I said, okay? Also, the moon. Its mass is much higher, you know, because cheese is pretty dense. So it's 7 times 10 to the 22nd kilograms. And I'll also let you know that the moon is 3.8 times 10 to the 8th meters away. That's all the information you need to know. We're going to just focus right now on 1, 2 in the number line. Okay, 1, 2 in the number line. The hint I'm going to give you is the meter stick's mass works nicer as 2 times 10 to the negative 1. That's my first hint. So hint 2, it's not even a hint. You probably already know this. What operation do I need to do? I need to do division, right? Bigger thing divided by little thing to see how many fit in there. So I need to do 7 times 10 to the 22nd divided by 2 times 10 to the negative 1. So right there's how we got. Let me review it again. One more time. We could do the 7 divided by 2 to get a 3.5. 10 to the 22nd divided by 10 to the negative 1 is 10 to the 23rd. Quotient property tells us I can subtract my exponents here. 22 minus negative 1 is 23. It's an incredibly large number. Our factor of 10 on the high end needs to be 10 to the 24th. Each one of these is a 1 times 10 to the 23rd. So 2 times 10 to the 23rd. And right here's our 3.5. So next, pretty easy to tell. I told you that the moon is 3.8 times 10 to the 8th away. Will this get there? What's like the quick, easy way to tell that's going to get there? Does a 3.5 tell us at all? No, but look at these factors of 10. How many? 23 factors of 10 here?
22
and 8 here. So what I want you to do to make this a little easier, what is true about these two numbers?
Well, it's obviously...
They're pretty close?
It's going to get there.
Yeah, but these two are pretty close, right? So treat them as the same number is my advice, okay? To answer this. I want to know how many times further than the moon it'll go away. How many times further? Do that with your pod, please. So, check out the fraction or the division I'm going to set up. I'm going to say something like, I'm going to do all my meter sticks, so I'm writing with a highlighter. 3.5, I'm going to call it 4. 4 times 10 to the 23rd, sorry. And then I'm going to divide that by how far the moon is away once, which would be I'm going to say 4 times 10 to the 8th. Would everybody agree this is roughly distance all my meter sticks go divided by to the moon once? So when I do this division, what happens to the 4s? Okay, gone. And 10 to the 28th divided by 10 to the 8th is 10 to the 15th. Which would be 10 to the 15th times away. Which is a huge number. That's a 1 with 15 zeros after it. Times further than the moon. That's kind of a crazy big number, right? I think I heard a 15 out there. Did it come from this?
Yeah.
So this isn't 15 times. This is times 10, 15 times. Or 10 to the 15th. What is that? 3, 6, 9. Is that trillion? Let's see. I don't think so.
9 is billion.
Yeah, billion. 12 is trillions. Is quadrillion a real thing?
Yeah.
So it's a quadrillion times further than the moon. That's really far. Okay. I'm not sure if a quadrillion is a real thing or I just made that up when I'm trying to say more than somebody else.
What's after quadrillion?
I wonder how many light years that is. Oh, that's question 4. So, to frame up question 4 with you, we want to know how many light years out these meter sticks are going through space, okay? But here's the deal. How far are they going? Do you remember? Let's make sure we frame up our question right. How far are the meter sticks going into space? Yeah, for this purpose, we're going to go back to the 3.5. But 3.5 times 10 to the 23rd. Because each meter stick is a meter, right? So I want you to figure out how many light years out they're going. So what operation do I need to do to see how many light years are up in here? Ivy? Yeah, I'm going to divide this by 10 to the 16th. Right? So I take my total distance divided by 10 to the 16th, which is 1 light year. You guys know what a light year is? It's how far light goes in 1 year, which is far. Do you know why you know it's far? Because light is like instant. It's like instant. So how far instant goes in 1 year? Here's how many years this is going to go for.
Oh my.
3.5 times 10 to the 7th.
So that means
35 million years the light would need to travel to get to the end of these meter sticks. That I know.
how would you just wait?
So we've got
If I drain this lake, I could
we've got 10 to the 8th for our high exponent. Each one of these is a factor of 1 times 10 to the 7th, 2 times 10 to the 7th, 3 times 10 to the 7th, 4 times 10 to the 7th. So I'm right here in the middle. It's kind of jumbled up with my work, but that's just what we're working with. So a point I'm going to make is if we dealt with raw numbers for all of these, how difficult would the computation be? Harder or easier than looking at our factors of 10? I think it'd be much harder to look at raw numbers. Guys, the hardest computation we did today was maybe 23 minus 8, or 7 divided by 2. 23 minus 16 being 7, yes. What I'm saying is, this is a way that we can really take huge numbers and make them nicer to work with. All right? Okay, who can tell me what they circled at their table? Ari? What'd you guys circle? You circled water, ice, olive oil? Anybody circle something different? Oh, same table? Livia? You circled water, diamond, ice, olive oil. Okay, anybody circle anything different? Josiah? Ice, water, olive oil. Okay, I'm going to circle all the scientific notations. You ready? And that's it. So, remember, in scientific notation, the first number needs to be greater than or equal to 1 and less than 10. Because where are all of our factors of 10 housed? In the power of 10, in the exponent of 10.
So it has to be in between 1.
It has to be greater than or equal to 1 and less than 10. So, as we look at space, how can I make that number a number between 1 and 10? Where would the decimal need to go? To make 300 million a number between 1 and 10, where would the decimal go? Vinny?
Just to make 300 million?
Yep, I need to make it into a number between 1 and 10 first.
Yeah, it would need to go after the third number, right?
So right here, 300 is a number between 1 and 10.
Yeah. Oh, no, yeah, that's what I meant. Like 3.
After the 3, so I'm going to write 3. And how many times would I have to move the decimal to get it back to be 300 million? 8, yes. So thanks, Rat. 3 times 10 to the 8. So there's that number in scientific notation. The first number is a number greater than or equal to 1, less than 10. All my factors of 10 are housed in my exponent now. So looking at 280 million. How can I write that one in scientific notation? Troy, what does my first number need to be?
Oh, I found it. Okay.
2.8.
First number.
Which one?
Copper.
Oh, okay.
Yeah,
Maybe
2.8. I need the whole thing. Okay. So how many times did I move the decimal to put it there, Troy? One move.
Back. Oh.
Would be right there. 1, 2.
Discounted.
8.
Oh, it's drawing from the right, not the left.
Either way, 8, right? Because if I multiply 2.8 by 10, 8 times it gets back to the original spot. Okay. Diamond, who can help me with that one? How can I write that number as a number that's greater than or equal to 1, Sean? 1.24. So I moved my decimal 2 more times, though. So it needs to be 10. 2 more than 6. 8. Okay. Olive oil. What am I going to rewrite 0.2 as, Cam? What am I going to rewrite 0.2 as? 2. And to account for that move, I now need to raise my 10 to the what power?
Would it be 8?
Yep, because 1 less.
Yeah.
2 to the 8. So here is why exponents and scientific notation are the bomb.com. As these look, pretty easy to tell what's the littlest, right? Boom, right there. Pretty easy to tell what's the biggest. Boom, right there. If you just look here, not as easy at all. Now, what if you had another number that was something like this, like 3 times 10 to the 9th? You instantly know that this number is the biggest or smallest. Which one? Biggest. It's got a whole nother factor of 10, right? We also found with our earlier computation, if we can use division with our factors of 10, it was pretty nice. So we're going to house all of our factors of 10 that we can in the exponent when we're doing scientific notation to make the computation easier. The whole point is to make it easier. Okay, here's the review. That's in scientific. This would be 4.82 times 10 to the 4th. This would be 9.9 times 10 to the negative 1, 2, 3, 4. This would be 3.6 times 10 to the 6th. This is scientific. This would be 7.8 times 10 to the negative 4th. There you go.